Well, we are waiting. Either some of among you that have figures that I want to show for a round table. Raise your hands if you do.
Hi. I just have an update for the receptive fields of the mesoscope modality.
Okay. Okay. Any others in the group currently? Alex?
I I can post the repo. I have I have a few things that mostly are AI generated, but some of it might be useful to discuss.
Okay. I see there are a couple new faces that I haven't seen. Antonio, do you want to introduce yourself?
Sure. Can you guys hear me? This is my first time on the
Yes.
meetings.
Yep. Welcome.
I worked on the predictive processing data set back on Janilia at Neurodata Rehack with the help of Carter. And I just basically started analyzing LFP data from the predictive processing data set. And I wanted to contribute and continue working on this project because, at least for me, it seemed really, really interesting. So I noticed that you are all making the data release paper, so I will want to contribute with some figures and stuff. I'm still just like having some preliminary figures with the LFP data regarding the standard oddball task and stuff.
Yeah, thank you. Yeah, we'll keep some time to discuss. Is there any other new people that are interested in speaking? If you are, please raise your hands or feel free to speak.
Yeah, I don't think I've been here before. I'm Ido. I'm a PhD student, soon finishing with Idan Segev and Mickey London from the Hebrew University, and I'm interested in dendritic computation. So I was interested in this project for the SLAP2 datasets, hopefully together with calcium imaging. And to contribute to this paper, I started to do some QC of the SLAP2 dataset with only the glutamate imaging. So hopefully next time will have something to present about it.
Great. Anyone else has just a half a minute introductions on things they want to show today or speak to? I just want to get a sense of the content.
Yeah, hi, I'm sorry, you can go first.
Oh no.
Yeah, please.
Oh, okay. Or
You mind?
Oh, so yes, I do have figures that would be relevant to, I believe, the figure 7 and figure 8. With respect to figure 8 and 7 will be with respect to the mesoscope data. So I have receptive fields to show with respect to the mesoscope data where I computed them from the receptive field mapping block. And in addition to that, for figure 7, I have an analysis that computes the representational stability across recording sessions, but also across subjects as well. And I can talk about those results. And yeah, that would be
Great. You hang? You want to speak? I'm not sure I'm saying your name correctly.
Yeah. Hi, I just wanted to introduce myself. I just finished my master's project with Professor Sarah Rudiger. Yeah, and I'm actually a pharmacology major, but I've been really going into the neuroscience direction recently. And when I was looking for a bit of another project to do, she suggested I hop on this and work on it with her a little bit. So that's it. That's
Okay.
it.
So you're just starting. Great. Welcome. So let's see. I'm going to give I'm just going to go quick minute to remind where we are on the manuscript, and then I'll probably poke a few people to try to sort of let them present what they have. We have a fair amount of material from what I hear, so let's try to be organized. So our manuscript is currently here. Last week, we merged the current authorship list. So if you feel like you contributed, I remind everyone that there's a link here to fill in your contribution, and this has to be approved. And then it has not changed the main content. These panel here will probably change by the end of this week. So Carter is leading there. We are going to make an update, especially in the SLAP 2, and a couple of changes in the Mesoscope, just to continue sort of fine-tuning the final session. Also, not promised yet, but Casper's lab is going to have a little more SLAP 2 session in the rest of the year. This has not changed. We had it with segmentation viewer, but I think might be helpful for some of you to understand the data. So Beast has 3 tabs that show how the data is constructed for each modality. So you can click on any ROI and see an exemplary trace on the right. Similar for a mesoscope, and the unit extraction here is dynamic. And so you can see the spikes as little dots on this line built on top of the raw data. So if you want to navigate and understand how the unit extraction is done, this is helpful, and it will be part of the manuscript. And then this has not changed. There's a contribution from, this has not changed. We do need to make a change on this figure because we realize that it's flipped. So actually the probe should be on the left. This is a mistake. We're going to figure it out. And this is a figure that I think David and Carter are working on. If we have time, I'll let them speak. And then there's an auto-tagging figure that we are iterating with Roberto De Filippo, but I don't think he's here today. And there's some mistake that we need to correct with him probably. So we'll sort of iterate on that. So the other things I want to bring up to your attention is last time Alex and a few others brought up to me the issues of collaborative editing. So I made this little platform here, but it's hosted on a server that allows to sort of collaboratively edit a MIS file. I'm not going to make this available quite yet because we need to sort of have a better solution for hosting, but it's going to come. Okay, so let's go back to those figures. I wonder if it makes sense to go from top to bottom. So unit extractions, this SNR questions, was there anyone here that had a content to these? Is it Marcel maybe? Or you were on receptive field?
Yeah, I'm more on the receptive field side.
Similar to Nicolas. So why don't we start there? Why don't you present Marcel for 5 minutes, and then same for Nicolas, so because they overlap, as I understand.
Yes, I would agree with that. They seem to overlap. Yeah.
Okay. Can you see the presentation?
Yeah. Yes.
Great. So I thought in case we need a little recap of how the pipeline of the analysis for the zebra stimulus works. Should I briefly summarize what the idea behind that is?
Yeah, it's a round table, so don't try to go too much into that. We want to favor discussion.
Okay. So here in this figure we have the zebra stimulus, and what I basically do is I convolve this zebra stimulus with all sorts of different Gabor filters. And these different Gabor filters, they have different properties. So they have a position, they have an orientation, they have different sizes, they have different frequencies, and they also have different phases. And I do this with all sorts of different filters, with all of these different properties, and I get out of that these activation maps. And what I simply do with these activation maps is I take one position of this activation map, and I just compute the correlation between the signal coming from this activation map with the signal of coming from a neuron, whatever that is. And out of that, I get basically spatial correlation maps. So to which position on the screen is the activity of a unit correlated to? And in the past, I, as a signal here coming from neurons, I used the spike, so the ethos, and that is something I've shown you. So basically how the majority of the results are going to look like is here on this left column. I will show these correlation maps. So I will call these receptive fields, and you can see them for two different phases. The according filters are plotted here in the second column, and you can basically see the difference between the phase 0 and the phase p half. And then for these two different phases, I show my results for both trials we have in the experiment. And having that, you can also do some sort of optimizations. So you can change the duration of the signal you're integrating over. This is here the third column called the duration. And you can see here on the y-axis basically the absolute maximum of this correlation, spatial correlation map for different durations I'm integrating over, the duration I'm integrating over. And in the last column, I'm optimizing the delays. So typically the information would need some time to travel from the retina to the regarding cortical area. And you can basically also optimize this. So basically you optimize the position relative to the stimulus onset. So the window, the position of the window and the length or the width of the window you're integrating over to compute this correlation here. So what I've showed you the last time I've presented was basically this enormous figure. So these are just like the top examples from 3 different probes from the neural pixels. And what you can see, so this just for getting you ready for the next slide, basically. What we talked about is that what we can see or what we can find are nicely located receptor fields. Some are smaller than others. And what was kind of interesting to see also is that the probes that which were aimed for example, primary visual cortex, showed like lower delays or smaller delays than, for example, here the what we find on probe D, what was aimed for later cortical area. So what I did in the since then is to do to repeat this kind of analysis with the mesoscope data, and I'm basically showing you the same plots, but for this other modality. And here I'm showing first of all for the primary visual area we have here. I ordered these 4 different columns after the depth of the plane. And what we can see when we like have a broad overview is that fortunately I also find nicely located receptive fields here. I hope the size is big enough. If not, then I can also zoom in.
That's okay.
I just want, because we already talked about all of the details, I just wanted to give the overview. Okay, I find receptive fields. I think this is the most important message here. And I also find some kind of optima when I do this optimization over different delays and different durations. Here, the optimization for different durations is a bit more like broad, because the sampling rate is much lower here in this case. So there's not much room to optimize, so to say. Yeah. So for the same, of course, I can also do for the with L, and also here I can see, or I can find like nicely located receptive fields. And in the next slides, I would just summarize some of these findings and some summarizing plots. So before I do this, do you have some questions for these mass plots? These basically just to illustrate that, okay, there's something. Okay.
Yeah, you have similar. Are the results distinct between the mesoscope and NeuroPixel, or they are just aligned grossly?
This is something I didn't do yet, but I plan to do, because what I wanted to do next is basically you can now summarize, for example, what are the typical delays you can find. And through all of these different planes, I see that like I find the maximum alignment of these convolved signals with the mesoscope signal after a delay of 100 milliseconds. There's one outlier. This is this VisL6, which has like a very low number of regions of interest that passed the filter of a maximum absolute correlation of, I think, 15%. So this is, for example, something one could try to compare with the results from the EFIS, but I'm not sure, for example, for the delays, how much similarity I would expect there. Something that would be more interesting maybe is the average receptive field size.
Yes.
So this is also something I can do, and I'm plotting these here for all of these different lanes, and I have a summarizing histogram here to the right. And as I understand it, I think it makes sense. So what I see basically is that for VisL, I see, or I didn't do the statistical test yet, but it seems that like the receptive fields tend to be larger than on primary visual cortex, whereas I don't see any differences for these different delays, for example, which I also would expect here. Don't get confused about these weirdly looking error bars. These are because I'm testing on a concrete grid. So when I'm showing like the same plot, but on a like each individual data point, you will see these are basically different sizes I'm testing for. And because of this concreteness, basically, when you do the bootstrapping, you can't end up with these weirdly positioned error bars. But I checked it; it's correct. So when you want to have a look on all of the results, these are basically that's the slide for it. And one could think of whether we want to test on a finite grid. But I think for like showing averages and so on, it's good enough, I would say.
Can I provide sort of higher level feedback?
Yeah.
The intent, well, I mean, you could go very deep in this analysis as a follow-up study. The intent of the data release is to highlight that this deep is possible. But what we really want to highlight in the manuscript is that you have a receptor field or things like that that are extracted by Zebra, and so we could add a supplementary figures to explain the process, like those that you show. But the reason we added Zebra in the first place was that we fine-tuned the stimulus to allow mapping system identification properties across pyramidal cells and inhibitory cells. And for instance, what I would totally expect is that on the mesoscope, where we have pan-neuronal imaging, you should see very different distribution of size tuning because we have many more inhibitory neurons that have very distinct, especially in the size tuning and the spatial temporal tuning of the units. And so, for instance, I could totally see a figure in this manuscript where you show the comparison distribution of size tuning between the neuropixels and the mesoscope. And based on first principles and what is known, they should be distinct because neuropixels and our recording in mesoscope have different bias.
Okay.
So I would encourage you to go in that direction.
Yeah, so I would like to do this comparison anyway. We can then discuss whether it should end up in the paper or not. Like, this right now is just for like proving that in the end, I think it makes sense, the analysis so far. One thing that one plot that should end in the manuscript is the average receptive fields, which we wanted to compare between different modalities. And what you can see here basically is that I do different thresholding for different absolute amounts of correlation values I find in these spatial maps. And this is something I also showed very similarly for the EFIS analysis. So basically, when you have very or no thresholding, then basically everything more or less averages out, and the very significant receptive fields don't have enough impact, let's say, to see anything. So you need some sort of thresholding. For example, here you say, okay, the minimum amount of correlation I want to have is 20%, for example, and then you start to see also like significant average receptive fields. And as I said, like this was very similar in the EFIS analysis.
Yeah. So where would you start if you were to contribute 2 figures to the data release? Where would you start given what you've shown?
So definitely to the receptive fields figure. We have this column for the zebra there. I also did the analysis for the local Gabor patches for the EFIS. I didn't do this for the mesoscope yet. This is also something I could deliver, let's say. More or less like the whole figure I wanted to contribute to. And then it depends a little bit what is missing until then, and yeah.
What about something that explain how to analyze zebra? Is that worth adding?
Yeah, I think we talked about that during the last time I presented. So definitely, I also would add to the text itself, obviously, for the things I contributed. Back then, so from my last presentation, your last impression was that maybe it was a little bit too detailed, and it could be worth to do a separate study out of that. And I definitely thought about it, but I'm not too sure currently whether it's like enough or not.
Yeah.
So I think in the end, I would say it should be like a, I don't know, group decision how much we want to go into detail there. I'm definitely open to explain in very detail what I've done.
Yeah. David, did you raise your hand?
No, I accidentally clicked the hand raising.
Okay.
Sorry.
I think showing the receptive field makes sense to me, and Zebra is sort of a key component of the stimulus design and is very new, and so I feel like explaining or showing just a first pass at extracting meaningful signal from those stimuli, I think will be valuable, and you could decide to continue it in much more depth on your own. That will be my feedback. I don't know if others have thoughts there.
Yeah. So basically, how the analysis works must be explained anyway, right?
Yeah.
Yeah. And then I think I like the idea to like leave it a little bit open what potential other scientists can do with it. But I think the most important thing would be to show that for each modality and also for each of the both stimuli we see receptive fields, we can also, for example, think using the zebra stimulus for orientation tuning, which I think you also wanted to include, if I remember correctly.
Yeah, will be valuable.
Yeah.
I think Alex has some things there to show.
Yeah.
Okay. Why don't we let Nicholas? Do you need more feedback, or do you feel
No,
like you have?
no. That was the very brief summary.
Okay. Nicholas, could you share what you have? Try to keep it within 10 minutes so that we give more time for others. And we'll have another round on this next week, so don't worry if you couldn't speak today. We will continue.
Here, can you hear me?
Yep,
Okay, and you can see the presentation as well.
that's right.
So I was focused on the OFIS data, and I looked specifically at the receptive field mapping block, so not the zebra stimulus. So I'll move past this slide. My analysis focused on looking at population level activity across these different views or planes. And the objective then was to make use of this population level analysis to look at specific receptive fields and how they contribute to the different population modes identified by the PCA analysis. This is just a diagnostic figure. I can move past this for the sake of time, but what we're seeing here in this figure, each row corresponds to a different plane, and each column corresponds to a principal component. And what we're seeing here is we're seeing the principal, the tuning of the population with respect to these different PC components for these different planes, where if the score in the PC component is higher than 0, then it means that that population is more tuned with respect to that PC component. So in addition to that, I have the receptive fields of these individual ROIs, where in this case, I took the ROIs that exhibited the highest, in this case, the highest PC2 score, and I plotted their receptive fields in the stimulus space. So I suppose to reiterate, the x-axis corresponds to a position in the screen where the stimulus is shown to the mouse. In addition to that, these receptive fields have been averaged over the different orientation stimulus presentations. In addition to that, I took these different PC components and I projected them onto the imaging field, essentially like where, onto the pixel space where we're imaging the neurons themselves to see the extent to which the different PC components, well, I want to see the extent to which we could see clustering. That is, if similarly tuned neurons are located in similar spatial locations. So yeah, so that's the result of that analysis. In addition to that, I was looking at the stability of the representation across recording sessions for each mouse, as well as the stability of the representation across subjects. The intent was to see, with respect to the stimulus tuning of these different populations across these different planes, how similar are these patterns of tunings across recording sessions and across different mice. So I will say, like, before I get into this, what's nice about the method of analysis I use, central kernel alignment, is that even if the ROIs differ between different planes, or between, of course, like different subjects as well, central kernel alignment is not sensitive to that, since it's only looking at the representation of these populations with respect to the conditions. But in any case, what we find here with respect to this analysis is that as the depth increases, in this case with respect to the primary visual cortex, the stability of the representation across recording sessions increases for each subject. So what that means is that as the depth increases, we expect the pattern of tuning across the population to be more similar. And we see a similar result with respect to the lateral visual cortex across these different subjects. So finally, I also looked at the stability of the representation across different subjects. The analysis method, I won't go too much into detail, but essentially I looked at how similar is the representation with respect to these different planes, how similar is it across the different subjects. And so what we're seeing here is something that is similar to what we saw in the previous slide, at least with respect to the lateral visual cortex, that as the layer depth increases, the representation is more similar across subjects.
That's
Yeah.
something I can also confirm that I see when I compute, like when I test like for how much correlation I find between the stimulus and the activity of a region of interest, then that for this like medium range of depth, for example, here, for example, here the 150 micrometers, I find the most amount of correlation, or the highest correlating results.
And that's with respect to the your analysis of the zebra stimulus.
Yeah.
The depth effect is interesting. I would be interested in seeing that in EFIS. Yeah, because you can do the same, right?
Yes. And it's particularly nice because the analysis method is not sensitive to the type of ROIs included. CKA is used a lot for comparing representations across different machine learning models with different architectures. So it's a useful analysis method when we're dealing with similar condition tuning, but the ROIs in question may differ between recording sessions or between subjects. But yeah, it can also be applied to EFIS.
Because there in the literature there's all of this hypothesis that deeper layers of the representation are all higher. Yeah, so I would be curious to see if it's consistent in EFIS, but okay. I will let you finish your track.
Oh, so that's this. I have some supplementary material, but that's the end of my presentation.
Okay.
So I think
I'm going to ask you
yeah.
the same question as Marcel. Is if you were from this, if you were to think about two figures that would make sense in the context of the data release, what would you suggest?
I would suggest the within subject stability of this figure I have here, since it's showing how stable the representation is across recording sessions. So for instance, if this number was very low, that would suggest that there's a lot of differences with respect to the population tuning across recording sessions. So I would say this figure. In addition, I think I'm very partial to this figure since it captures the population level tuning and the different the different axes in which that population level tuning varies. In this case, we're looking at PC2 to PC5. The labels are a little small, but they can be increased in size. So I would say either this figure or this figure if you prefer something that's more focused on individual ROIs.
Yeah,
the
figures on chronic is very nice because it shows one with specific aspects of the mesoscope, which is the chronic recording, right? We really have 8 sessions per mouse, whereas the receptor field, to be useful, I think you might have to apply this PCA approach to other modalities, right?
Yeah, I do have a pipeline in place for that. Yeah.
I think I would advocate for doing as you said, this chronic figure, but just on mesoscope and the one with receptive field PCA, maybe across the 3 modalities, if possible.
Yeah, and I could generate this figure here with respect to the different modalities as well. That's feasible.
Yeah, you could try. Yeah, you could try. Okay.
Okay.
Do you feel like you have good guidance, or do you need more inputs from the group? I have more questions for Nicholas.
Yeah, just excuse me, real quick. Two things real quick. So the first is the PCA approach. I think it would be great to plot the components. It's very difficult for me to wrap my head around if I don't know what PC1 is or PC2 is.
Oh,
And
yes, you're
often
referring to the PC loadings?
right, I want to see the components. But you
Yes.
can just plot your component. And so I think it's especially helpful to do that in neuroscience because often you see, oh, it's just a DC shift or this is the initial transient. Or so, because we think about things in a certain way already. It's a matter of abstraction and linking it back to something more concrete that we have more intuition to. But I might be missing the point here entirely. But each time I see a PCA analysis on neural data, to me it's helpful to see the actual principal components.
So you're referring to these, for instance, these PC loadings that.
So so maybe I got it wrong. So I thought you computed the PCA for the time series.
I computed the PCA with respect to a matrix that I computed where each ROI has a number of columns which correspond to the different conditions. And for each of these conditions, I get the average responsiveness of that ROI.
Okay, then scratch that. Sorry, I missed that entirely. Okay, that's okay. So I thought you did a PCA over the time series, the activation, but no, that's not what you're doing. Okay.
Yes, I should
The
have
second one,
clarified that earlier.
yeah, I think so. So it's interesting. Now the second one with what you saw with the deeper layers, it seems to me that this may be too much for the data paper, but it actually may be worth developing that in a whole paper by itself. So because it's interesting and it sounds, and I don't know exactly, it sounds new. So there is this whole field already on representational drift, which is kind of what you're getting at, right? So you kind of said, okay, how stable is that? What you call a representational geometry. We could bicker about what we want to call it, like the pattern of activation, right? And you can spatial pattern of activation. And so there is already this whole work by the Allen Institute on representational drift. And I'm mentioning that because, especially here, it's going to be important to show, for example, that, hey, this is not trivial because the upper layers have more heartbeat. And so things are changed. You know what I mean? Like there's more work needed to convince a skeptical reader that this is real, that the difference between the upper and lower layers is not because of something trivial. It could be explained by the physics of the upper versus lower layers. So I could see that this would have to be a more involved paper. But to show that representational drift is less in the lower layers than the upper layers. So maybe adding also better precision on which layer it is exactly. If you do current source density, you could probably tease out what is below layer 4, what is in layer 4. Sorry, this is pretty high up layers. But you might still be able to find out what layer 2 is versus 3 or something. And yeah, and adding maybe the neurophysiology to it, you could go for the entire column. So anyways, I'm just saying this sounds interesting. It might be worth this whole paper.
I agree with you. I think that it wasn't clear to me what the interpretation of the increase in representational stability would be as depth increases. So I agree with you.
There's a lot to say. So I've been working on columns. So for example, layer 1 is mostly just inhibitory neurons. So the computations, if you want to call neuroprocessing this way, it should be very different than layer 1, for example, right? And then the difference between layer 2 and 3 is kind of really interesting to think about. There's a lot of research about it. Now, if you get into layer 4, for example, then the argument could be, well, that's the low-level input. And so that has been less modulated. There's less cognition or less feedback. And so that should be maybe more stable because this is, more deterministic, if you will. So there's all kinds of ways to kind of discuss it and think about that. That's why I think it might be its own paper because it seems to be extremely interesting. There's old work, by the way, that shows that. So I know this is just the upper layers because this is all optical imaging, but there's really old work.
No, Alex, you misguided. We image down to the layer 5 here.
Oh, okay, cool. Yeah, that is super interesting. So there's very old work that, for example, suggests it's very disputed that orientation tuning is very variable in V1 in the cat was most of that work done in the lower layers. And so it was very disputed and people wash it away. But I see that now in neuropixels recordings in mice, that if you do orientation tuning across the entire column, the lower, it's pretty much exactly where layer 4 ends. You see that the orientation tuning doesn't seem to follow the column very often. So you get the same orientation tuning and then very different tuning in the lower layers. And so back then there was a lot of debate about, how straight is your probe compared to cortex, because if it's not exactly orthogonal but tilted to cortex, you might cross into other orientation columns. But this shouldn't bother you with what you have here, but it might get to something deeper about different layers and so processing along the column. So I think it's super interesting. It might be worth its own paper.
Yeah, I was wondering, with respect to these different layers, I could find metadata on their layer depth, but I couldn't find metadata on their their location on the cortical, with respect to the cortical surface, their XY position, their Z position. I could only find metadata on their depth.
Yeah, we could improve that in the documentation. Boost areas, so the 2-photon is positioned at the center of the respective area, and you should have the depth in that area. We have a figure in another manuscript that we could link that explain how the depth relate to the layer, but obviously layering is in the cortex is not an absolute science with imaging, and so knowing the boundaries between layers is sometimes difficult, especially in the mouse between layer 2 and layer 3 is not clearly defined, and so we are always been careful there. But I do want to mention that we image quite deep because the brain is a little compressed due to the preparations. Yeah, we can improve the documentation. Okay.
Would you say that the layers are like what we're seeing is that they're stacked on top of each other?
That's right.
And so if I were to look at layer, in this case, if I were to look at the primary visual cortex at 120 micrometers, that would be sitting, I suppose, above this.
So which number did you choose here for the depth? Because there are many sessions, or is it one mouse?
No, these are each of these lines corresponds to a different mouse.
Yeah. But typically the way we position the instrument is the top layer should be in layer 1 with majority of inhibitory neurons. The second layer should be in layer 2, 3. The third depth should be in layer 4, and the last one layer 5.
Okay.
But pending mouse to mouse and session to session variability, that could be slightly off, but that's the intent. And we've calibrated this with Cree lines where we knew that this was layer 5 cells with RBP4 Cree line. And so we verify those depth. And so those have been used for years.
Okay,
so
and has that been documented?
In the context of showing plots across many mice, I would just put the numbers 1, 2, 3, 4, and because the depth is going to be irrelevant across mice.
I see. That makes sense. I can do that.
Yep. Do you feel it? I mean, it seems like you have to iterate with two figures, the receptive field and the chronic. I think I'm on the same page as Alex, but this could grow into a whole study. I still think there's value in showing any chronic analysis across session. So if you could make a minimalist version of this that show that the response is stable across session, that will help us because it support the design.
Okay, yeah, I can do that. My code is set up so I can run it on all the modalities, so I can do that.
I think Jerome is specifically talking about the image. Can you go up? So I think what Jerome has in mind, or what I would have in mind, is if you could show your CKA or something as a function of all the 8 sessions. Let's say you pick one mouse, and then you compute the stability of the the representational geometry for all the 8 sessions that it got imaged. So you get a time series. You see
That's right.
how.
Yes, I think I do have a figure like that, where what you're saying is compute the CKA with respect to all of the layers, we could say, and compute that with respect to each of the recording dates, so we can see how the similarity of the representation varies across recording dates when, or something along those lines. Is that capturing what you're saying? Like a heat map, for instance, could do that.
Yeah, that makes sense. It's great. I do want to keep some time for some of the newcomers.
Yeah, I can stop sharing now.
Thank you, Nikos. This is fantastic. Could we just speak quickly with Antonio, because I think he was starting to do things that were interesting, and I just want to make sure he leaves with some guidance. Antonio, you were starting to work on LFP, is that right?
Yes. I have some like really basic figures, but I was also planning on start working with, for example, layer specific like LFP signatures, quality metrics and stuff. But if you want, I can present super shortly. It's really short.
Well, yeah, I just want to that you leave with some instruction that will be helpful, because and then we can let and then we can let Alex present. But I feel like there's going to be more next week probably.
Okay. Yes, yeah. Some instructions will be amazing of what the expectation for some kind of LFP figures would be.
So do you have something to show, or you want to have a conversation?
I do have a little bit of the preliminary analysis, but it is just super short. So if you want, they can present it then.
Yeah,
it's like super short.
Will be great. Anything is fine. Draft is okay.
Can you see my screen?
It's loading content for me.
Okay. Is it already showing or not yet?
I see a black screen.
Let me send again. Maybe if I share my whole screen.
Maybe it could be the bandwidth. I'm not sure.
Probably. So this is my entire screen. Can you see the presentation? Okay.
That works.
All right. So this is work that I did on Neural Rehack around 3 weeks ago with the predictive processing data set, which at the time was just a really basic analysis that was if we have some kind of prediction errors or novelty signatures on oscillations on the visual cortex. It was just one area at the time. So what I did is I took some of the traces of the oddballs and some of the traces of the standard stimuli, and I performed a PSD analysis, super basic. And what I found was that on oscillations around like 20 to 30 hertz, there was an increase on the power of this kind of like gamma-ish power on when the orientation change, right? So as you might see on the first figure is just a PSD with an increase on gamma power during oddballs and a decrease on the power during the omissions. And that on the middle panel is just Hilbert transform across time. And as you might see during the stimulus, there is an increase on the power of gamma. Even as you see on the side, there's also an increase. That's leakage from other trials or other stimulus presentations. And as you might see on the omission, there is a lower power of gamma. This seems to be that the gamma rises at stimulus, and when it's not present, there is no an increase in gamma. However, it seemed to be increasing more on the orientation oddball stimulus. So this is for the standard oddball mismatch. For the sensory motor mismatch, there's also an increase when the orientation changed from 45 and 90 degrees, at least on the PSD. And there's all the Hilbert transform. And on the sequence mismatch, it got a little bit more messy because the sequences evoke some different kind of oscillation patterns. And some of the takeaways were that the gamma signature of the visual cortex, I just choose layer 2 tree specifically just to like iterate faster. It was at our 9 animals at the time that had the locations with 3 distinct paradigms. And there seemed to be not a general novelty, but stimulus violation type, right? With specific signatures of the only when the orientation changed, there was this big increase, and when the stimulus was absent, there was even a decrease on the power. Yeah, so that was it. It was just like again some really short stuff.
This is great. I actually think you could make a nice figure out of this on the LFP. Yeah, so like a highlight the LFP data as the first row, and then show your analysis of the frequency, right? And then an exemplary response, and then across the context. I think that you have a beautiful figure here to make.
Oh, thanks. Yeah, no, I would absolutely love to do that. I'm still trying to wonder if I could do like one area or at least the main areas that are on the paper: prefrontal cortex, visual cortex, and some of the motor cortex.
Well, for instance, the sequence has very little response. I would expect if you go to the probe in the front, you're going to start to see more response. But that's a research effort. But I think just showing in V1 is perfectly fine. You were just highlighting that there are responses in the NFP data, and the intent of the data release is just to highlight that this data set is worthy of more investigation. So a single figure on the LFP just to highlight, and then we could add also a little dynamic viewer to sort of help people understand the LFP data. So it could be just a beautiful self-contained figure.
Oh yeah, I love that. I'm gonna try to see if I can work on that and have some kind of prototype for next week to see to show a little bit of the data processing and data like online. See, just to make people see that the LFP could be useful for some kind of analysis as kind of like a broadcasted error signal, something like that.
Okay. Alex, do you feel like you could present your result next week? Does that make sense? Or
that's probably better, actually. Yeah.
Yeah.
There's only one thing, maybe to Marcel and also Nicholas, anybody who's working on receptor fields. I'm wondering if we can come up with an ID, especially for actually for all modalities. If you compute a receptor field, let's say for a neuron in the neuropixels data, or for a ROI potential neuron in the mesoscope data, in one mouse, one session, I wonder if we can come up with a unique identifier some kind of ID, so that if I compute the receptor field using a different technique, I can go find the same neuron. And then we can compare these receptor fields.
For the ethers, we already have this identifier, right? And then for the other modalities, we can just say something like session, blah, 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 row, blah, blah, blah.
Yeah,
Right,
I think I think ROIs in the Mesoscope data already have IDs of some kind. It might just be their index in the like ROI table.
Yeah, it's the index.
Yeah.
But that means it's not unique.
Yeah, you designate it by session, like by session and then index, right?
Yeah, that's exactly what I wanted to say. For ethers, it's unique.
So I suppose the ID should include the subject, the session, and by session I mean the recording date, and I suppose the index, well, also the plane as well, but the index for the ROI and the plane, if that's not already included in the metadata, which I think an ID like that could be put together.
Yeah, I think what would be great is maybe if we could schedule a meeting like in a couple of weeks or so where we could compare, like to get ready until then, so we can easily access the results of the others, and then compare whether we get the same results or not.
That would work for me.
Then, so you want to meet among yourselves or within that group?
I think that would be a meeting dedicated to the receptive field analysis. So I would think whoever's involved in that can meet together to see how do our results align, how are our methods differing from each other.
Yeah. Do you want to organize then via the forum simply?
Yes, yeah. The forum can work for organizing that.
Okay. And for next week, so we're going to start with you, Alex, and then are there others in the group that want to make sure that they have time? I wonder if some of the people that didn't speak today, if they have any questions or comment before we depart. Yes, C.
Hi, my name's Caroline. I added like some intro to the discussion, just like to introduce ourselves last week. I'm interested in like analyzing some of the data sets, but yeah, I said I would come to this meeting. I'm just wondering like how I could get started, like where you guys need more hands on deck. Yeah, nice to meet you all.
Nice to meet you. Well, the manuscript, you can go in many directions. So you see that people are exploring on their own initiative somehow. But so, for instance, you could choose a modality of interest and look at a specific oddball response. I think that will be valuable. In terms of things that we have not covered, so receptive field, I think we have a fairly decent group. I think the effect of the oddballs on the behavior is something we have not looked too much. So you could look into that. If you're more interested in neuronal response, I think looking at differences across contexts is something that Antonio started to look at, but there's a lot more to do in the NeuroPixel data probably. It's up to your interest a little bit. This data is very rich.
Oh, okay, perfect. Yeah, I didn't know if it was like just, investigate yourself or like if you guys like assign things. So yeah, I just wanted to like get a sense.
Yeah, it's a bit grassroots.
Okay.
So we try to self-organize. But what is your expertise? Do you have a particular modality with more expertise?
I mean, so just to like give some background on me, like I've done a lot of like wet lab experiments in neuroscience before I switched over to computational Like I majored in computer science at Columbia. And so, yeah, when I first got started with like computational neuroscience, I didn't really know how to code all that much. I was very early on in my coursework. And so I figured that this would be a good way to, just get a little bit more experience on this side. Yeah, so I did like connectome analysis stuff primarily when I was like starting out a couple years ago. I went to Microsoft for 2 summers. I'm doing some like computational cancer work right now, like as my job. So I really enjoy the study of neuroscience. I feel like there's so much to learn, and the brain is obviously very interesting. So yeah, so I would say I'm somewhat of a beginner in this field, but I've read papers on like representational drift and stuff like that. So I'm just trying to combine all of my experiences in this endeavor now. So
Yeah. What do you think, Alex? Should we have a more focused session with her, or?
Yeah. Also, you might want to post in the discussion forum. I think Nicholas also just posted a link, and then we can offline we can discuss a little more about what you might be interested in, what has been done, what hasn't, because I agree that right now it's difficult to get an overview. And then maybe see if you're maybe more interested in the LFP, the spiking, the imaging. And also there's a big opportunity here maybe for vibe coding, AI coding. So and we have, I think, a lot of material that you could, for example, just hand an AI, and the AI can take it from there. So yeah, so maybe the forum might be a good way to get started.
Okay, great.
Yeah.
Yeah, I was planning on watching some of the former YouTube videos that you guys put up, like maybe the last 2 or 3 weeks, just to get a lay of the land. But okay, yeah. Okay, yeah. I guess how do I get in touch with you guys? Is it by email or
The forum.
the forum? Is it the
Yeah,
discussion?
because I think we like to use the forum because it allows everyone to participate, and there's no walls. And so I try to be on top of it. Sometimes I miss some thread, but if some leaks through, you can send me an email. It's fine. And Jerome L at alleninstitute.org. But I would prefer to use the forum because everybody can follow.
Oh, I guess because you guys mentioned doing something offline.
Oh, if people wants to meet among ourselves, it's fine.
Okay. Okay.
Among themselves, it just this meeting is meant for everyone to come in and make sure that you're onboarded and.
Okay. All right. I'll start taking like a proper look at things, and I guess I'll be in touch.
Thank you.
Okay, great. Thanks.
Anyone else with questions before we depart? I'm sorry, Ito and Yu Hang, we didn't get a chance to. Yeah. Ito?
I was just wondering if there is going to be receptive field analysis for the SLAP2 data, if it makes sense.
I think Yu Hang should speak to that because Sarah Rudiger has done a lot of work there with her colleagues. Maybe I don't know if she. Yeah, I think next week I think Sarah is going to be back, and I think they were working on the SLAP2 analysis a little bit. I encourage you watch a couple of previous sessions that were dedicated to SLAP2 because we have done a little bit of work there, and that might catch you up, and because there's a lot more to do.
Okay, sounds good. Thanks.
Any other questions?
I suppose we can organize the receptive field analysis meeting over the discussion forum. I think if Caroline wants to come and observe, that's fine as well. If you'd like to see how that happens.
Yeah, that would be great.
Great.
Oh, when does that meeting happen?
Oh, we'll be deciding on the discussion forum.
Okay. All right. I'll keep my eyes peeled on that discussion forum. Thanks.
Thanks, everyone.
Thank you.
We'll meet again next week. It was great. Lots of
See ya.
material.